Thank you, Dr. Tan, for introduction. I'm very happy to be able to do my presentation here. I'm Hirono Ohashi. I'm a postdoc at Tokyo University of Agriculture. In this lecture, I would like to explain this based on a paper that has already been published in IEEE Sensor Letters, with figures could be not published due to page limitations. So it's my first time oral presentation at an international sensor conference, so I am very nervous. Please be gentle with me. First, today's content. First, I will introduce contact position method. Sorry. Yes. Method and their problem. Next, I will explain objective based on these problems and explain the proposed method. And then I will talk about the result of indentation experiment and summary and future experiment. Soft sensors have been developed to acquire various contact information such as pressure, contact position, shearing force, and strain. A sensor that estimates the contact position is necessary for stable gripping of the robot. Formation flexible contact position sensor identifies the contact position by arranging arranging pressure sensor which are excellent at point measurement in a grid pattern and checking which pressure sensor are responding. Currently, a method called impedance community has been developed that identifies the contact position by arranging conductor channel in a grid pattern. However, when the measurement range is expanded, both contact position sensor require more wiring to connect elements and the sensor to the measurement equipment. As the number of wires increase, the structural and functional problems arise. Structural problems include an increased risk of wire breakage and less of elasticity, which is a characteristic of soft sensors. On the other hand, function issue included the complexity of calculation required to estimate contact position and electromagnetic noise generated from wiring that affects measuring results. Therefore, less wiring is a necessary element for contact position estimate sensors. Soft tactile sensor using conductive materials or sensor elements have been applied to impedance topography, and various types have been developed to enable perceptive interactions with surrounding environments. In this tactile sensor, a pressure-sensitive channel filled with conductive materials is embedded in an elastomer. The deformation of this channel, which provides contact information from the sensor, is quantified by measuring channel resistance. However, multiple tactile parameters include contact pressure and position cause resistance changes at the same time. So it is not possible to classify multiple tactile parameters. Therefore, a method is needed to classify these contact parameters. So the objective of this research is to develop a software sensor using conductive materials having less wire and be capable of easily classifying information on the contact position and pressure. Therefore, one the characteristic of soft tactile sensor using contact materials is that the sensor property is changed by the channel design and these materials. Therefore, we wonder if we could solve these problems by the channel design. So we constructed a soft tactile sensor in two channel fields with conductive materials crossing and parallel to each other. In the next slide, I will explain the manufacturing procedure of the proposed sensor. First step is here. Pour and cure silicone into a plastic mold and remove the silicone rubber from the mold after curing. Next step, sand were created by dissolving rods made of water-soluble alcohol. This means water-soluble PVA in hot water. And next step, insert the silicone tube and copper pipe into the sensor body and eject the ionic gel before curing. Last step is illustrated FD. The ionic gel was cured by irradiation with ultraviolet light. Inkjet material these. In next slide, I will explain the working principle of the proposed sensor. When the tactile sensor is pressed, the ionic gel channel deform and the resistance change. The resistance change is affected not only by the contact pressure but also by depth from the ionic gel channel. When contact pressure is fixed, the deeper the ionic gel, the smaller the channel deformation and the resistance change. When contact, if the two channels are arranged as shown in the figure, the resistance change in channel 1 increases as the contact position moves in the positive direction of the x-coordinate, whereas the resistance change in channel 2 decreases. Therefore, we consider that the ratio of the change in resistance for two channels increases monotonically from the left-hand side to right-hand side for the sensor. And the contact position can be simply obtained by calculating the ratio. It has been reported that resistance change can be expressed by the following formula. The change in resistance depends on indenter size, the depth, cross-sectional area, surface area of the channel. Also, if the contact position is known, the pressure can also be obtained using these formulas. Therefore, we conducted an indentation experiment to verify whether the proposed method was correct. We measured the channel resistance using SL meter by changing contact position and depth. The indenter moved along the x-axis from -30 to 30 meters with an interval of 2 millimeters. The contact depth Z was varied between 1 and 3 millimeters from the top surface of the sensor instead of 0.5 millimeters. The difference between the resistance value measured before pressing and the resistance value measured during pressing is defined as delta R. There is the result. Figure A and B presents the mean and standard deviation of the resistance channels observed in channel 1 and channel 2, respectively. These data indicated that delta R1 and delta R2 increase depending on a channel depth and pushing depth. Next, we calculate the ratio of resistance change in the two channels from delta R1 and delta 2. The results are shown in figure C. As shown in the figure, the ratio of resistance change for two channels increased monotonically from the left to the right as expected. Based on this graph, we estimate the relationship between radio and contact position. However, the contact position can be obtained by simply calculating the ratio to this formula. However, data from the pushing depth of 1 millimeter were excluded from fitting because the standard deviation was large. Next, we performed the same experiment and the contact position was obtained using this formula. The horizontal axis is the actual contact position and the vertical axis is opposite. Vertical axis is the estimated contact position. Since the value of the correlation coefficient is close to 1, it was found that the estimated contact position and the contact position are almost the same. Furthermore, the pressure was calculated using the contact position and equation 1 and 2 shown in 9th slide. The figure shows the estimated contact pressure at each contact position and depth. Additionally, each straight bar line shows the pressure value measured at each contact depth. Among each pushing depth condition, the estimated pressure near the center of the sensor is close to the actual value. Possible cause of error in the estimated pressure are error in estimating the contact position and an oversimplification of the theoretical formula for the resistance change. This is a summary slide. I like to summarize as follows. The objective of this study is development of soft touch sensor having less wire and be capable of easily classifying information on the contact position and pressure. Therefore, we fabricated the sensor with 2-channel arranged crossing and evaluate its performance through indentation experiments. As a result, we found that the proposed sensor can estimate the contact position and pressure. In the future studies, we plan to continue improving sensor sensitivity and develop sensor applications. This is the last slide. I'd like to thank Dr. Furukawa and Dr. Yoshida at Yamagata University for useful comments and providing ionic gel. And this work supported by JSPS. That's all for my presentation. Thank you for attention.